Dear someone, nice to meet you. My name is Claude, and I'm a gas cloud. I'm writing this letter because something in my life is going to happen, and will change it forever. I don't know exactly what's going on, and yet I feel something. Actually, I can't tell if this is a good or bad sensation. I feel like something is attracting me, and I can't escape it, not even if I would. But at the same time, I'm not afraid. I spent a big part of my life orbiting around what humans call a black hole event horizon. A black hole is a well-known and respectable object in our universe, and we, the gas clouds, orbit around them all of our life. We, the gas clouds, don't know exactly why we are here and what's next. Every day's a new adventure for us, but we don't know that some of us start to stretch slowly and then get eaten by the black hole. One day they're telling jokes and dancing with us, orbiting around the black hole. The other, they take a dangerous step in a dangerous direction. The process starts. Anyway, we don't know much about it, because once the stretching or spaghettification process, as humans call it, takes place, our cloud friends can no more communicate with us. They just slowly fade away. During my journey around the black hole, I've seen many of them going and never coming back. And they didn't even say goodbye, because they couldn't. But I remember that sometimes before they got swallowed by the black hole, some of them said to me that they felt like an attraction to the center of it. And now I feel it too. That's why I decided to write this letter to you. I want you to continue studying what the hell is going on here and why gas clouds disappear. I think everyone is here for a purpose, and maybe ours is to fade away, plunging into the black hole to bring new knowledge to you. We are sure you won't disappoint us. This is what a cloud orbiting just next to the event horizon of a black hole would write if it could send a letter to humans. How do I know that? Follow us on this video to get to know more about what happens at the event horizon of a black hole. The event horizon is part of a black hole. In plain language, it could be described as a point of no return. It is literally a comical prison that not even light itself can ever escape, a threshold behind which no events can affect the observer. But to understand more details about the way the event horizon is conceptualized, we need to talk about the context of astrophysics, namely the theory of general relativity and black holes, with whom the concept of the event horizon is closely associated. What's the role of Einstein's theory of relativity? At the event horizon, the escape velocity is equal to the speed of light. Since general relativity states that nothing can travel faster than the speed of light, nothing inside the event horizon can ever cross the boundary and escape beyond it, including light. Thus, nothing that enters a black hole can get out or can be observed from outside the event horizon. Likewise, any radiation generated inside the horizon can never escape beyond it. So the fact is, you should watch your step, because one step could make the difference. In fact, let's suppose you are approaching a black hole, and you are an astronaut and wanted to communicate with your spaceship. If you are one step away from the event horizon, you could still communicate with someone and receive some signal from your crewmate on the spaceship. But as soon as you cross the event horizon, you are screwed. No more signal, no more communications. The electromagnetic waves you are trying to send are traveling at the speed of light, but they will never reach the spaceship. Actually, they would take an infinite time. Now the question is, where is the event horizon? How to find it? Fortunately, we had some great scientists and mathematicians that have been studying this subject all over the past decades. One of them was Carl Schwarzschild. Even if you don't know who Schwarzschild is, if you're a scientist enthusiast, you've certainly heard of him before. That's because he solved Einstein's field equations. The physical parameter that shows up in the solution is called the Schwarzschild radius. The Schwarzschild radius, also called the gravitational radius, is the radius below which the gravitational attraction between the particles of a body must cause it to undergo irreversible gravitational collapse. This phenomenon is thought to be the final fate of the more massive stars. The Schwarzschild radius for a given object is the Schwarzschild radius equals to 2 gm over c squared. where g is the gravitational constant, m is the object mass, and c is the speed of light. For a mass as small as a human being, the Schwarzschild radius is of the order of 10 to 23 centimeters, much smaller than the nucleus of an atom. For a typical star such as the Sun, it is about 3 kilometers or 2 miles. According to this, in theory, any mass can be compressed sufficiently to form a black hole. The only requirement is that its physical size must be less than the radius of the event horizon. For example, our Sun would become a black hole if its mass was contained within a sphere about 2.5 kilometers across. What does this have to do with the event horizon of a black hole? Well, the solution of Einstein's field equations corresponds to the radius defining the event horizon of a non-rotating black hole. What Schwarzschild actually found was that the solution contained terms of the form 1 minus Schwarzschild radius over r, which becomes singular as r equals 0, and 1 over 1 minus Schwarzschild radius over r, which becomes singular at r equals rs. Rs is the Schwarzschild radius, and the first singularity, r equals 0, turned out to be a physical singularity that cannot be removed. Every time we have to deal with a singularity, something is messing up. This is exactly what happens as you reach the event horizon. Everything is messed up. As we said, the Schwarzschild radius applies to non-rotating black holes, and rotating black holes have distorted non-spherical event horizons. It should be said that since the event horizon is not a material surface, but rather merely a mathematically defined demarcation boundary, nothing prevents matter or radiation from entering a black hole, only from exiting one. Once you're in, you're done. So we've just learned that the event horizon effectively hides the singularity at the center of a black hole, a boon for astrophysicists discomforted by the breakdown of the laws of physics at such a point. Abraham Loeb, the chair of astronomy at Harvard University, accurately described the event horizon as the ultimate prison wall. One can get in, but never get out. How do we study what happens at the event horizon? Let's suppose you're observing the behavior of a gas cloud close to the event horizon. The event horizon could be then described as the last stable orbit outside of which gas can still radiate away. We see the light, and then inside this event horizon, radiation can't make it out. Here, space and time change their properties, so events change in their sequence of what happens. This is something very funny and unexpected. To resolve the event horizon and see what happens there, we have to wait for an event at that horizon. We use the same method as meteorologists use on Earth to calculate how the weather is evolving, and we simulate the physics of a gas cloud or gas using hydrodynamically equations, the Navier-Stokes equations. We do a simulation of a cloud moving around the black hole, and then we try to observe the physical phenomena in the real world. We are always kind of being corrected by observations, and that helps us to tune our model so that we get the conditions right, and then we calculate iteratively what will happen. Then again, an observer has to look carefully to see what happens close to this last stable orbit, close to the event horizon. What do we find? Before finding out the answer to this question, be sure to like or dislike the video so that we can continue to improve and make these videos better for you, the viewer. Plus, be sure to subscribe to the channel, clicking the bell, so that you don't miss any of our weekly videos. We predicted that clouds should have been stretched as in a spaghettification process. And guess what? We found that clouds were getting spaghettified. We saw indeed that we can apply meteorology to the universe. Isn't it amazing? Of course, there are a lot of things we can't explain yet, but as years pass by, we will be adding more pieces to the big puzzle of black holes. An event horizon is a fascinating place because it is the prediction of general relativity, but at the same time, it is a quantum object. Quantum mechanics and general relativity cannot be unified because general relativity is not part of quantum mechanics, and quantum mechanics predicts that everything is extended, and general relativity says that the event horizon is infinitely thin. So when the gas enters this last stable orbit, we expect to see new phenomena which combine general relativity and quantum mechanics in a new theory of quantum gravity. We might learn something about this new theory. That's why studying the event horizon is an object of critical importance. How do we observe an event horizon? In order to observe an event horizon, we have to arm ourselves with powerful telescopes with an angular solution comparable to the event horizon. That's why we started an international collaboration, the EHT. The EHT is an international collaboration that has formed to continue the steady long-term progress on improving the capability of Very Long Baseline Interferometry, VLBI, at short wavelengths in pursuit of this goal. This technique of linking radio dishes across the globe to create an Earth-size interferometer has been used to measure the size of the emission regions of the two supermassive black holes with the largest apparent event horizons, Sagittarius A star at the center of the Milky Way and M87 in the center of the Virgo A galaxy. In both cases, the sizes match that of the predicted silhouette caused by the extreme lensing of light by the black hole. The EHT project includes theoretical and simulation studies that are framing questions rooted at the black hole boundary that may soon be answered through observations. By linking together existing telescopes using novel systems, the EHT leverages considerable global investment to create a fundamentally new instrument with angular resolving power that is the highest possible from the surface of the Earth. Over the coming years, the international EHT team will mount observing campaigns of increasing resolving power and sensitivity, aiming to bring black holes into focus. The Event Horizon Telescope was designed to capture images of a black hole, and it has succeeded. Since April 10, 2019, we can admire the picture of a black hole, but black holes can't be seen. What we actually see in this famous picture is how the event horizon of the M87 black hole bends and captures light. If immersed in a bright region, like a disk of glowing gas, we expect a black hole to create a dark region similar to a shadow, something predicted by Einstein's general relativity that we've never seen before, explained chair of the EHT Science Council, Ino Falk of Radboud University in the Netherlands. This shadow caused by the gravitational bending and capture of light by the event horizon reveals a lot about the nature of these fascinating objects and allowed us to measure the enormous mass of M87's black hole. That's all for this video. Thanks for watching, everyone. Do you think we will understand more about the event horizon of a black hole? Did you enjoy this video? What's your favorite black hole? Let us know in the comments below. See you next time on the channel.